we have to think beyond those pictures. You know, those entanglement already something hard to imagine or to think about. And but we have to not only we have to think about entanglement, we have to think about the so-called long-range entanglement. And here, so the picture I described here are all shorter entanglement or unentangled. Then you may say, what is a long-range entanglement? Well, I explained that for the spin system, if you sum over all up and down spins, if sum all up and down spin configuration, we actually get a spin state where spin all point to the x direction, which is unentangled. So therefore, we should sum over spin configuration, but we should not sum over all configuration. If you sum over all configuration, it's unentangled. If I do not do any sum, certainly this is also unentangled. So one idea is that to sum a partial configuration, we sum over a subset of a spin configuration to obtain this long-range entangled states. Okay. So one way to do so is to start with a spin system where we view downspin as our background. Then we say the upspin only from loops or from strings or loops. Okay. Only consider those kind of configuration where upspin from loops. And then when you do the superposition, we sum over all this loop configuration. So this way, we do not sum over all spin configuration. We only sum over a partial sum of a spin configuration, only loop of upspins. So this way, we get some kind of a state. And certainly, this is a long-range entangled state. Okay. And we can also allow string to branch. So if you only consider loops, then just loops. However, we can also make this loop to have a branching, you know. And we can also sum over some subset where loop can branch. And so that's kind of string net. Okay. So this is string net also kind of a long-range entangled state. So those are basically give us some long-range entangled state. There are some kind of interesting wave-function, interesting states. Then the claim is that this kind of we call the string liquid state. This kind of string liquid states somehow is what we want, and this kind of entanglement, long-range entanglement, can explain this sixth wonder of our universe. How? You know. So here I try to explain why the long-range entanglement of a string liquid can explain the existence or origin of the electromagnetic wave. You know, electromagnetic wave actually coming from this kind of string liquid. So, so let's look at the superfluid first. The superfluid actually is not a string liquid, but a particle liquid. It's a superposition of all position of particles. So superfluid wave function is superposition of all particle configurations. That's ground states. To obtain excited states, we just deform this kind of wave function by saying we make a wave where somewhere we have more particle, somewhere otherwhere we have less particle. So we have a density wave. And this kind of deformation of ground state by particle density can propagate. And this propagation of a density of a particle are described by Euler equation, some simple wave equation. Okay. And so therefore, that's it. So that's a wave in the superfluid, which is described. That's a Euler equation. Okay. And this could be our world. But interestingly, that the photon in our world is not described by Euler equation, but described by Maxwell equation. If you imagine, if a photon in our world are described by Euler equation, we can claim our world is superfluid. Okay. But actually, it's not. So photons in our world do not satisfy this kind of Euler wave equation. So our world is not superfluid. But what? But actually, our world is a string liquid. It's a string liquid it's described before. That's like a string formed by upspins, something like that. Okay. Then how to understand why Maxwell equation can come out from string liquid? So we can say that in a string liquid, just like a particle liquid, it's a superposition of all kind of loop configuration. That's a strings. Okay. Then you say, then what is a wave in a string liquid? Well, very simply density wave of strings. So somewhere we have a more string, otherwhere we have a less string. But however, the string density is not a scalar. The string density is a vector. So here I have to point out that the string liquid we consider here is the string have an orientation. It's an oriented string liquid. So I didn't draw the arrow because it's too hard for me to draw all those arrows. So those strings are oriented. So when you say some region have more strings, you have to say more string in which direction. Okay. So the string liquid, the string density have a sense of direction. So actually it's a vector. Okay. And then there's also saying that but the loop liquid also have a property. If a string are in this direction, we cannot change the string density in the direction along the strings. Because in order to change the string density in the direction along the string have to end. String have an open end. But our string here, our loops, there's no open end. So the string cannot change, density of string cannot change in the direction along the string. But the density of a string can change in the direction perpendicular to the string, like here. The string can in the vertical direction, but density would change in the horizontal direction. So that really means that the string density have this property that it have a zero divergence. So therefore, it have only two transverse mode. So therefore, the density wave in the string liquid is very interesting. It have no longitudinal mode, have two transverse mode. And that's exactly what we have, because this is like a spin one boson with two components. This two transverse mode is two components. Okay. And this wave, the wave equation to describe a wave with only two transverse mode but no longitudinal mode is naturally Maxwell equation. Actually, Maxwell equation is the simplest wave equation to have this property. And so therefore, basically, that's it. So Maxwell equation basically is an equation to describe a wave in the string liquid. We know that when Maxwell first proposed his equation, people immediately ask what kind of media supporting electromagnetic wave. And people even gave this media a name, ether. Even though we gave this media a name, ether does not mean they exist. So people looking for ether for a long, long time, for 150 years, and did not find it, and we write this in textbook that ether do not exist, but still there's question, what is the origin of an electromagnetic wave? And since after this 150 years looking, we didn't find it, so what do we do? Okay, here we do. We declare electromagnetic wave is a fundamental. So fundamental means don't ask. So basically, we don't ask. And so I remember when I learned this, I did ask. So teacher tell me over and over again it's fundamental. So I say, okay, it's fundamental, so I don't ask. And so what I try to say is that your first doubt actually probably is correct doubt, no matter what the teacher says. And so we know that in our world, not only we have an electromagnetic wave, we call the U1 gate theory, we also have a weak interaction and a strong interaction, which are described by so-called the Yang-Mills theory. And here I just want to say that using the same picture, we can understand the Yang-Mills theory as well, because we simply assume the string have some different types, and the different type can join certain way. And by assuming string have how many types and how they joins, you actually designing this gauge group. For different choice of string type and different joining condition, you actually get different gauge group. So that's how we have SU2 gauge theory and SU3 gauge theory. It's just from the so-called string net. This kind of generalization from loop to string net allow us to obtain non-abelian gauge theory. Okay. And actually we get even more, because certainly, so right now we are facing a situation that here I claim our world is an information world, and our space is qubits. you don't have to believe it, because the other theory saying U1 and SU2 and SU are fundamental is also a theory, and you can take that theory, say they are fundamental. You should not say it's a qubit. They are fundamental. Don't ask where it comes from. And so why thinking this gate theory as emerging from qubits? Why this is why we want to do that? Why don't we just say they are fundamental? Then don't think about that. Why? And, well, I don't know why. But however, thinking this interaction, this gauge field as an emergent, actually can allow us to understand more. Here we can also understand emergence of electrons. So although we try to, at the beginning, we only try to understand where origin of the photon, but when we're using qubits to understand origin of photon, we automatically understand origin of electron without further assumption, without additional assumption. Okay, and the story goes like this. The loop, we assume our vacuum is like a loop, liquid, quantum liquid. It's a liquid of a loop. It's a string liquid. Okay. And then in the ground state, we only have loops. But when you have open strings, what happens? Well, when you have open strings, you may think that this open string is like an extended object. But however, remember, this open string is in the background of many, many loops, just like here. There's a background of many, many loops. Then the middle part of the open string kind of merge with this background loop liquid. So it's hard to see, whether this string is a part of open string or part of closed loop. So what I try to say that when the open string is inside the loop liquid, the middle part costs no energy. Only the two ends looks different. So only two ends cost energy. So actually the open string do not like extended object. It's like 2-point object. So therefore in the loop liquid, there is a defect, a point defect, which actually corresponds to end of a string. And this end string is like this. And remember that the end string actually is a source of string density. Remember, we say that when you only have loops, the string density have no divergence. The string density actually is the electric field. But when you have a string have an end point, then the divergence with string density or divergence with electric field no longer zero, and the source is end of string. So therefore, end of string behave like a charge of the gauge field. Okay. And this kind of charge can be boson or fermion. If the string liquid wave function is an equal weight superposition of all string or loops, then the end point is a boson. But however, if you modify the wave function, we say actually the string liquid states is a superposition of string configuration, but with some kind of plus minus amplitude. Then the end string would have a different statistic, which is fermion. So actually, statistics is not a fundamental property. It's just a different wave function. If a qubits have a different wave function, then the open string, the end of open string would have different statistics. Okay, and this plus minus sign have the following rules. We can project three-dimensional string liquid to the two-dimension. Then this projection would loop make cross. Whenever you see a loop crossing, we have a minus sign. So you just count how many loop crossing. We have a total even number of loop crossing, we have a plus sign here. We have a total number for all the loop crossing, we have a minus sign here. If you're using this way to assign the sign for the wave function, then the end of string will change statistics from boson to fermion. So this is the recent progress. So therefore, using string liquid, we can really unify this gauge interaction and the Fermi statistics. So gauge interaction, like Coulomb's interaction, and the Fermi statistics actually is the same phenomena of quantum entanglement. It's a particular Lagrange entanglement can give rise to to gauge interaction and the Fermi statistics in the same framework. So that's what we say there's a unification of gauge interaction and the Fermi statistics. Okay, and maybe let me just quickly mention this. Is that you know, this qubit theory actually, or stringlet theory, is really lattice theory. And for a long time, people believe that when you have a lattice theory, you cannot have a chiral problem. You cannot have chiral boson or chiral fermion. Basically, you cannot produce a phenomenon where gauge interaction only interact with the right-hand fermion, not interact with the left-hand fermion. So this kind of chiral property can never be produced by some lattice model. So this is the reason we believe that, because people working for, I don't know, for 30 years, 40 years, and don't get that. So we say maybe that's it. But recently we find that this is not right, and actually we can do that. And so basically, this chiral fermion, this qubit theory can produce chiral fermion. But however, we have the modified standard model. The standard model have a 15 wild fermion per family, and that one probably cannot be produced by qubits. But however, if you modify standard model, say there is a 16 wild fermion per family, then this version of standard model can be produced by qubits. Okay. So therefore, this chiral fermion problem can also can be actually produced by stringlet theory. So that's okay. And so basically, to summarize that, we can view our world as a space as an ocean of qubits. So it kind of, our space really like the ocean, but it's ocean of qubits. And then this qubit is not, but however, not just arbitrary ocean of qubits. These qubits form a stringlet. I mean, basically, these qubits entangled in a certain way. You know, if qubits entangled in different way, we will have different set of elementary particles. So you can imagine we have many different universes where qubits have different entanglement. Then the elementary particles will be different. In our universe, the qubits should be entangled in a certain way. We call the entangled in a way we call the stringlet liquid. And in this kind of qubits ocean, the fluctuation of stringlet gave us a photon, the gluon, etc. The end of a string will give us electron, the quark. So that's basically is a new world view in this second quantum revolution. And this picture can explain the first 6 properties. And but we are still trying to see whether we can get the 7th property. That's whether graviton can be understood from this point of view or not. So that's related. If you can understand the graviton, we can say that even geometry coming from long-range entanglement. Yes.
In this framework, how do you describe the interaction?
You know, it's naturally there. For example, the end of the stream naturally interact with density fluctuation, and that interaction happen to be Coulomb interaction. So basically, you just study stream liquid, like in the solid. In the solid, when you have a dislocation will cause distortion of the lattice, and the 2 dislocations naturally interact with some power law, have some power law interaction. Here's the same thing. When you have an end of a string, this defect naturally interact inside the string liquid, and this interaction happen to be Coulomb law. They can all be derived. So certainly I didn't do this, but once you assume this kind of ground state wave function, you're putting this end string there, you will automatically get a Coulomb law. So everything we know is produced. And sometimes I should say more, because I should not say we want to produce a Maxwell equation, because our world have no Maxwell equation. Because Maxwell equation is a semi-classical picture of the quantum world. So what we really have is quantum electrodynamics. Quantum electrodynamics have no Maxwell equation, have only Schrödinger equation. It is a semi-classical approximation of this quantum electrodynamics give us a Maxwell equation. So to derive a Maxwell equation, we cannot derive Maxwell equation. We have to say this qubits world have a semi-classical approximation, and in this semi-classical picture we have a Maxwell equation. So Maxwell equation really is a semi-classical picture for the quantum world. So this, but the qubit directly give us a photon, directly give us a photon, not macro equation.
But it still does not determine coupling strength and issues of metric.
Yeah. So this is a very, very good question. And so what do you mean by explaining our work? Okay. And so in particular, I should write down, there's a couple of fine structure constants 1/37. Should we explain 1/37 in order to claim we have a theory of our work? And at the moment, this is a philosophical question. And I try to say is that usually in the theory, we can explain integer. We cannot explain the value of a real number. It's kind of like, can we explain the mean distance between the Earth and the Sun divided by Planck mass? That's a dimensionless number. And so in the unit of Planck mass, the mean distance between Earth and the Sun is a dimensionless number. Should our fundamental theory explain such a real number? And since the answer is no, it's just accidentally that we don't explain that. So I'm thinking about maybe all the real number in the fundamental theory probably is something like distance between Sun and Earth. It cannot be explained, and so like electron mass, proton mass ratio, fine structure constant, all these dimensionless real number, probably cannot be explained. But however, there is a prediction. All the number which cannot be explained must be time dependent. So because like a distance between Earth and the Sun, we cannot explain that. We don't know. We cannot explain it has to be this. But if we cannot explain that, it is time dependent. That is indeed true. The distance between Earth and the Sun is time dependent. So, but I don't know whether this is certainly this is not. It's just some philosophical thought. Is that all the integer number, a rational number, can be explained like why quark have a charge 1/3 or things like that. But all these dimensionless real number cannot be explained, and it should be time dependent. And so actually that's my point of view. But this can be tested. Is that really time dependent? What determines this real number? So actually, the physics behind what determines value of a real number is really, really puzzling. And so that's why I'm thinking in that direction. Okay, maybe let me skip this. So basically, is that the message here is that the matter and information is the same thing, and this picture is possible, is consistent with our work because the quantum information have a long-range entanglement. Because of long-range entanglement, this richness, like a gauge interaction, Fermi statistics, spin 1/2, this kind of weird property can be explained using qubits, using these very simple qubits. Once we have long entanglement, all this strange property can be explained. Okay, so far I'm talking about Hannian physics. I'm supposed to talk about kinematic physics. So here, let's talk about kinematic physics. Okay, we know the kinematic physics is a very old field. Okay, and many people think it's too old. It's so old that we think we enter the beginning of the end of kinematic physics. So there's not much new thing to do. So except some kind of engineering application like optical fiber or blue LED. However, I feel that this picture may not be right. I feel that we only see the end of a beginning, not the beginning of an end. I'm kind of more optimistic. And so actually the exciting time is still ahead of us. Actually, I think we are now already in or entering the exciting time. And this time is as exciting as the time like from 19 and to 1930s. You know. And because why I think that way, because what I just explained, you know, we kind of seeing or making this second quantum revolution. So this generation is a lucky generation, you know, not like a Lambda. So we should feel lucky to be working in this generation. And but this kind of point of view. So in condensed matter, we feel we are entering into the very exciting period of time. It's coming from this study of quantum Hall states and or spin liquid states. So here's a picture of a spin liquid. And so the reason these two states are very interesting because for a long time we believe all the phase and all the phase transition are described by symmetry breaking. But however, the quantum Hall states and the spin liquid states, they all have the same symmetry. So there's no way to use symmetry breaking to explain these two states, these two kind of matter. So therefore, this means in addition to symmetry breaking order, we must have a new kind of order, so which we call the topological order. Okay. And the notion of topological order is introduced in 1989. But in 1989, you know, if you think back to 1989, the quantum computing is not fashionable, and you know, the quantum entanglement of qubits is not fashionable buzzword. So at that time, we did not realize topological order had anything to do with entanglement. But actually now, after the quantum information became very popular, after we learned quantum information theory, we realized that topological order is long-range entanglement. So this quantum Hall state and spin liquid state are very interesting because they contain long-range entanglement. And this new state matter really is a topological order, but which usually coming from a long-range entanglement. Okay, so here is a more precise definition of a long-range entanglement. As I already explained, the product state is not entangled. Okay. However, we can scramble the product state. Suppose we start with the product states. Then we perform some kind of unitary transformation between two qubits. We can rotate and scramble two qubits. And so then we create entanglement among these two qubits. So then you can use this yellow box to entangle those qubits locally. But when you do that, we create something so-called short-range entangled states. So short-range entangled states like a product state, but with some kind of local scrambling. Okay. And certainly can do some layer of local scrambling. So that gives us short-range entangled states. But our word is very interesting is that not every many-body states have this form. You know, there are some states which we call long-range entangled states, such that it can never be thought as the product state with some local scrambling. Okay, so this kind of state exists. So there exists some kind of long-range entangled states, but it's not local product states. But long-range entangled states gave us this new picture or new understanding of a quantum matter, because all the short-range entangled states are connected by this kind of quantum circuit. You know, we can doing this local scrambling to change one short-range entangled state to every other short-range entangled state. They are all connected by this local scrambling, and this we say they belong to same phase. Okay, but the long-range entangled states and the short-range entangled states cannot be connected by this kind of local scrambling, so they belong to different phase. So to go from one state to another state, we need a phase transition. But however, for long-range entangled states, we also have a situation that we have different long-range entangled states. So these two states are not connected to short-range entangled states via this scrambling, but they are not connected to each other. So there's a different kind of long-range entangled states. So this different kind of long-range entangled states correspond to different topological order. So this is how we use entanglement to understand the new quantum matter or new phase. So that's topological order. So with this definition, the next question is that what is the mathematics describing this? Describing long-range entanglement. And this reminded me of a story that I'm reading a popular science book when I was in high school. It's about a tribe which have four